Chapter 3.1 and 3.2, Trigonometric Ratios continued. As a reminder, we have sine theta equals the opposite side divided by the hypotenuse side. Cos theta equals the adjacent divided by the hypotenuse. And tan theta equals the opposite divided by the adjacent. In a right triangle, the hypotenuse is the side opposite the right angle. The opposite side is across from our angle of interest, and the adjacent side is touching the angle of interest but not the hypotenuse. We know that we can solve for a side length of a right triangle if we have the other two sides using Pythagorean Theorem. If we have an angle and one side, we can solve for another side using a trig function. We're going to do that here. So we want to label the side that we have and the side that we want. 17 is across from the right angle. That makes it the hypotenuse. And x is opposite the given angle. So it's the opposite side. Then you're going to decide which trig function to use based on those two sides that you labeled. So which trig function has opposite and hypotenuse? We can write out our SOHCAHTOA. Which one has opposite and hypotenuse? That would be sine. So we're going to use sine for the first question. Sine theta equals opposite over hypotenuse. Then we plug in our information. Our angle theta is 59. Sine of 59 degrees equals the opposite is x, and the hypotenuse is 17. Then to solve this, we can put a 1 under sine 59 to make it a fraction. Just going to put brackets around this angle. Then we have two equivalent ratios and one unknown, which means we can cross multiply and divide to figure out our answer. You always multiply the diagonal numbers first and then divide by whatever's left over. So sine 59, move out of the brackets, times 17, and divided by 1, which doesn't actually do anything, and we get 14.5718. Which gives us 14.6. Next one, label the side we have and the side we want. Side 20 is across from the right angle, which makes it the hypotenuse. And then from our angle of interest, side x is touching that angle, but it's not the hypotenuse. That makes it the adjacent. Which trig function has adjacent and hypotenuse? That would be cos theta equals adjacent over hypotenuse. Plug in our values. Cos of the angle 27 degrees equals the adjacent side, which is x, over the hypotenuse side, which is 20. Put a 1 under the cos 27 to make it a fraction. Then we can multiply the diagonal numbers and divide by our third number. Calculate cos in brackets 27, move out of the brackets, times 20, and dividing by 1 doesn't do anything here, so we get x is 17.8201 ... So rounded to the 10th, x is 17.8. In this unit, we round angles to the nearest whole number typically, and side lengths to the nearest tenth. Next one, label the side we have and the side we want. The side we want, x, is across from the right angle. That makes it the hypotenuse. The side we have is touching our angle of interest, but it's not the hypotenuse, so that makes it the adjacent. Which trig function has adjacent and hypotenuse? That's cos again. Cos theta equals adjacent over hypotenuse. Plug in our values. Cos of the angle, which is 51 degrees, equals adjacent side is 10 over the hypotenuse, which is x. Put a 1 underneath the cos 51 to make it a fraction. Then multiply diagonal numbers. Notice our variable is on the bottom this time, so our diagonal numbers are 1 and 10, so 1 times 10, which is just 10, and then divided by our cos 51. Calculate. 1 times 10 is just 10, divided by cos in brackets 51. Calculate, and we get 15.8905. So x equals 15.9. Next one, side 20 is across from our angle of interest. That makes it the opposite side, and side x is touching the angle but not the hypotenuse, so that makes it the adjacent side. Which trig function has opposite and adjacent? That would be tan, TOA. So tan theta equals opposite over adjacent. Tan of our angle, which is 40, equals the opposite side, which is 20, divided by the adjacent side, which is x. Put a 1 under tan 40. Then cross multiply and divide, multiply diagonal numbers, which in this case is 1 and 20. Then divide by what's left, which is our trig function. 1 times 20 is 20, divided by tan 40 gives us 23.8350. Rounded to the nearest tenth is 23.8. And last one. Our angle of interest is in the top right corner. Side 16 would be opposite that angle. And the x side is touching the angle, but it's not the hypotenuse, so it's the adjacent. Opposite and adjacent, that's tan again. Tan theta equals opposite over adjacent. Plug in our numbers. Tan of 69 degrees equals opposite is 16 over the adjacent, which is x. Put a 1 under tan 69. Then cross multiply and divide. Diagonal numbers would be 1 and 16, so multiply those. And then divide by our tan 69. 1 times 16 is 16, divided by tan 69, enter, 6.1418. To the nearest tenth, that rounds to 6.1. Solve for the following unknown angle, round to the nearest degree. So we're going to do a similar process to the last page where we were solving for a side using trig ratios. We want to label the two sides we're given. In the first one, side 44 is across from the right angle, making it the hypotenuse. And side 39 is across from the angle we're trying to solve for, making it the opposite side. Then using SOHCAHTOA, we want to decide which trig function we're using. First one is opposite and hypotenuse, which is sine. So sine theta equals opposite over hypotenuse. Plug in our values. We don't know our angle, so that's going to stay theta. Sine theta equals opposite is 39 and hypotenuse is 44. And then we want to move the sine portion to the other side of the equals, so we do our sine inverse to both sides. Sine inverse and sine cancel each other out. We get theta equals sine inverse of the fraction 39 over 44, and then we calculate. For sine inverse, we need second function and then sine. In the brackets, we want 39 over 44 or 39 divide 44. We get 62.4198. Rounded to the nearest degree is 62 degrees. Next one, 36 is across from the right angle, making it the hypotenuse. And 24 is attached to our angle of interest, but it's not the hypotenuse, so it is the adjacent. Adjacent and hypotenuse, which trig function would we use? That would be cos. Cos theta equals adjacent over hypotenuse. Plug in what we know. We don't know the angle, so that's staying theta. Cos theta equals adjacent is 24, hypotenuse is 36. We want to move the cos to the other side, so do cos inverse on both sides. Cos inverse and cos cancel each other out. We get theta equals cos inverse of the fraction 24 over 36. Then we calculate, shift cos brackets 24 over 36, or 24 divide 36, which is 48.1896. To the nearest whole number, that would be 48 degrees. Next one, 11 is across from our unknown angle. That would be the opposite side. And 28 is not the hypotenuse, but it's attached to our angle of interest, so it's the adjacent. The trig function that has opposite and adjacent is tan. Tan theta equals opposite over adjacent. Plug in what we know. Tan theta equals, the opposite side is 11, the adjacent side is 28. We want theta to be alone, so we need to get rid of the tan by doing tan inverse on both sides. Then tan inverse and tan cancel out, and we get theta equals tan inverse of 11 over 28 in brackets. And then we calculate that. Second tan in brackets 11 divided by 28, or 11 over 28. We get 21.4477, which rounds to 21 degrees. Last one of this type. In this case, we have all of the sides. We've got our hypotenuse, which is across from our right angle. We've got our opposite side, which is across from the angle we don't know and we want to find. And then the third side is the adjacent side. So how do we know which trig function to use? Well, since we have all three, we can choose any of the trig functions. So whichever one you'd like to do, I'm going to go with sine. So I'm going to use sine is opposite over hypotenuse, so I'm going to use the opposite side and the hypotenuse side. Sine theta equals opposite over hypotenuse. Sine theta equals opposite is 63 over hypotenuse is 87. We want theta by itself, so do sine inverse to each side. Sine inverse and sine cancel out, so I get theta equals sine inverse of 63 divided by 87. Calculate that. Second, sine in brackets 63 divided by 87. We get 46.3971, which to the nearest degree would be 46. Theta equals 46 degrees. In triangle ABC, angle C is 90 degrees, side B is 7.4 meters, and side A is 6.5 meters. Solve the triangle, round angle measures to the nearest degree, and side measures to the nearest tenth. To solve a triangle means to find all angles and side lengths. Let's draw our triangle. We have a right triangle. The 90-degree angle is angle C. The other two letters are B and A. Doesn't matter which one goes where. Then side B is 7.4 meters, so the side that's across from angle B is 7.4 meters. And that would be called little b, and it's opposite from angle B. Side A is opposite from angle A, and that is 6.5 meters. Now when we're solving questions in this unit, we want to try to use the measurements we're given for all of our calculations. It's not always possible. Sometimes we have to use a number that we've calculated for another calculation, but if you can, use the given measurements for all your calculations. So I need to find side C, which is the hypotenuse. I have two sides of a right triangle, and I want to find the third. So I can use Pythagorean Theorem. I'll do that over here. This is calculating side C. The formula is side squared plus side squared equals hypotenuse squared. C is our hypotenuse, and our other two sides are 7.4 and 6.5. So 7.4 squared plus 6.5 squared equals C squared. And then rather than calculating now, I'm going to square root because I want C, not C squared. So I square root both sides. And I get that C equals the square root of 7.4 squared plus 6.5 squared. Then I calculate that. Square root of 7.4 squared plus 6.5 squared equals 9.8493. And then we want to round side lengths to the nearest tenth. So C equals 9.8, and that would be in meters. So that's part of our solution. That's our missing side length. Now we need to find angles A and B because we know that angle C is 90 degrees. So it doesn't matter which one you start with. I'm going to go with angle A. I have the side that's opposite angle A. I also have side B, which would be adjacent from angle A. Opposite from A and adjacent from A. Which trig function would I use? That would be tan theta equals opposite over adjacent. Plug in our values. Tan angle A equals opposite from A is 6.5 and adjacent from A is 7.4. We want A equals, not tan A equals, so do tan inverse on both sides. Then tan inverse and tan cancel out. We get A equals tan inverse of 6.5 over 7.4. Then calculate second tan in the brackets 6.5 divide 7.4. Enter 41.2953. So A is 49.2953 ... or rounded to the nearest whole number for angles, A is 49 degrees. And last, solving for angle B. From angle B, we have our opposite side, which is 7.4 meters, and then 6.5 meters, that would be adjacent to angle B. We have side opposite from B and adjacent from B. Then we would use tan again. I'm just going to go ahead and plug in my values. Tan theta equals the opposite from B is 7.4 and the adjacent from B is 6.5. We want theta equals, not tan theta equals, so do tan inverse on both sides. Then tan inverse and tan cancel out. We get theta equals tan inverse in brackets 7.4 divide 6.5. And then theta equals, calculate that, second tan in the brackets, we do 7.4 divide 6.5, which gives us 48.7046, or to the nearest whole number, 49 degrees. Something doesn't make sense. Let's see. Angle A, I wrote 49, it's supposed to be 41. This is supposed to be a 41.2953, which makes angle A 41 degrees, and then angle B is 49 degrees. And the reason I knew that something was up was because the angles in any triangle have to add up to 180 degrees. Since C is 90 degrees, that means that A and B have to add up to 90 degrees. So when I saw that they were both 49, that didn't make any sense. So that's why I knew there was an error. A equals 41, B is 49. You can double check. 41 plus 49 equals 90, plus another 90 for angle C is 180 degrees. And that's true of any triangle. The three angles will add to 180 degrees. So we've calculated the two missing angles and the one missing side, so we have solved this triangle. That brings us to the end of Chapter 3, Lesson 2.